The purpose of Lab 3 is to find the mass of a black hole in which a star of a known mass and position is in orbit around. We are going to use the momentum principle and Newton's universal law of gravitation to do so, as well as find F-net in relation to position and time, and decompose it into parallel and perpendicular components computationally. My observed results was that the mass of the black hole was 3.18 times 10 to the 31 kilograms. This appears correct because my computational model was correct and WebAssign approved this result. The principles used in this lab were Newton's universal law of gravitation and the momentum principle. Newton's universal law of gravitation states that F-net is defined by G, which is 6.67 times 10 to the negative 11 Newton meters squared divided by kilograms squared, times mass 1 times mass 2 over r squared, which is the distance between the planet and the black hole, or the star and the black hole, which I sometimes refer to as a planet. This is seen here. The momentum principle is change in momentum equals F-net times change in time, which we can rearrange to be F-net equals change in momentum over change in time. As for coding, I put in my given initializations here. The initial mass of the planet is in kilograms and change in time is in seconds, and these were all from WebAssign. And this line of code down here pulls data from the file mbrushi3_gotek star data, which contains the planet's x and y position data, and this was also given by WebAssign. Now, finding the planet's velocity and momentum we have to do in order to find F-net. So before we start this iteration loop, which is going to find the velocities and momentums over all x and y components of our data, we have to do v equals position over time, and that was done earlier. And then right here, it separates our initial and final components of velocity into x and y components, and then finds the magnitude. Because p equals mass times velocity, we just simply multiply our initial and final velocities times the mass, and we get those. And our delta v and delta p, we just subtract the final or the initial from the final. In order to then decompose F-net, we have to understand what F parallel and F perpendicular are. So F parallel, which is also dp dt parallel, depicts how fast or slow an object goes, which is always tangential to the direction of motion. So this depicts a speeding up or slowing down based on d times magnitude of p over dt, and the tangential part is multiplied by the p hat right here. So that shows the tangential part. And this is right here going in the direction of motion. Now F perpendicular, or dp dt perpendicular, depicts the direction of motion or the curviness of this circle of orbit. This is defined by the magnitude of p, which is how great it is curving, and or which is the direction, and dp hat over dp over dt is how big it's curvy or how steep it's moving. Now, as for decomposing F-net, we have to apply the momentum principle to our velocity and momentum data found earlier, and this is Newton's second law. Newton's second law states that delta p equals F-net times delta t, so we rearrange that to mean that F-net equals delta p over delta t. So we find dp dt by dividing our change in momentum divided by our change in time, and then we set that equal to F-net, because F-net causes this change in momentum over time. Now, when we decompose this equation further, we get our F parallel equation and our F perpendicular equation. And we can easily apply those to the code here. Because this part of our F parallel component can be decomposed even more to our magnitude of P final minus magnitude of P initial over change in time times P hat, we put that into our code. And then we set F-net parallel equal to dbt parallel because they are equal to each other. And we do the same for F perpendicular because F-net equals F parallel plus F perpendicular, so we just subtract and get our F perpendicular. My orbit's averagation is seen here, where the red arrow is our F parallel and it is clearly tangential to the motion. Our F perpendicular is the blue arrow and it is pointing inwards towards our black hole, and it is always pointing towards the black hole. Our yellow arrow is the magnitude of them both, which is our F-net, because F parallel plus F perpendicular equals F-net. The results of my computational model showed that the mass of my black hole was 3.18 times 10 to the 31st kilograms. I showed it here in a rearrangement of the universal law of gravitation equation, which I just put in the in my code in the loop. If I hadn't put it in the loop, then my FNet and R data would be the last data pulled. Now, that would give me a lot of error because I had not taken the average. Because I put it in the loop, I'm taking the average of all the data collected, and not just the final, and then finding the mass. But because I have a limited amount of points given in my WebAssign data, then I still am going to have some error. Now, what does this mean? FNet is the cause, and dPdt is the effect. So if dBT parallel is non-zero, meaning that it's speeding up or slowing down, it had to be caused by a non-zero FNet parallel. And the same goes for dBT perpendicular. Now, what if the black hole, the mass was removed and a different black hole was placed in the same location? If the motion is unchanged and unaffected, then you know that the mass has to be the same. Because if the motion of the star remains unchanged, you know that FNet is affected directly by the mass of the black hole by the law of gravitation. So you know that the trajectory is affected by FNet because of the components of F parallel and F perpendicular. So you know that if the observed trajectory is changing by FNet, and FNet is has to be the same to create an unchanged trajectory, then the mass must be the same. Thank you.